Welcome everyone to this Minisymposium here. That's the second session we have on AI and HPC for CFD applications. My name is Andreas Lintermann from the Universal Computing Center. I'm the chairman for the session, and we already had one session today, and we have two more to come. One is tomorrow. I think it's in the morning or in the afternoon. No, it's in the afternoon. Thank you, Rakesh. And on Friday morning, there's also another session. So when we start with our first presentation here, from Michele Buccicotti, inferring turbulent parameters via machine learning. Stage is yours.
Thank you very much for the introduction, and good afternoon. So, I'm Michele Buccicotti from the University of Rome, Tor Vergata. I work in the group of Luca Biferale. The pointer is disappeared, but it's okay. Okay. And there, since a few years, we are trying to use data-driven tools to solve some open problems in turbulence, in fluid dynamics in general. And the problems we are trying to tackle are data assimilation problems, like, for example, reconstruction of flows with partial informations, or the problem of inferring parameters. And this is parameters of the flow. And this is the problem that I want to discuss today. So we will see in detail. So first of all, let's see what is the problem that we are interested in. And this is the problem of inferring the rotation rate of a turbulent flow that is evolving on a reference frame that is under rotation. So let's imagine this is the Earth that is rotating around this axis, and we want to study the effect of rotation on the flow, on the flow dynamics. So the system is described by the Navier-Stokes equations, plus there is the Coriolis term that depends on the rotation frequency of the reference frame. So it is known that this Coriolis term has an important effect on the dynamics of the velocity field. And in particular, if we look at the two-dimensional cut of the three-dimensional volume of this flow, we see that if rotation is not strong, it's, for example, omega 2 on 4, the dynamics is almost indistinguishable from the normal three-dimensional setup. So we have small scale fluctuations with the energy that is flowing in a direct direction. So from where it is injected by the forcing towards small scales. On the other hand, when rotation increases its frequency, we see that we have the formation of a completely different dynamics. So we have these large-scale vortex cyclones that start to appear in the velocity evolution of the flow. So of course, understanding whether we are below or above this transition, we have a sort of phase transition, is easy. I mean, it can be easily done by just looking at the velocity module. But what it is difficult instead is trying to identify what is the correct value of omega, which is observed inside, which was used actually inside one of the two sides of this transition. So when we have this inverse energy cascade, we have the formation of these large scale structures. And it is not simple just looking at this plane of the velocity field to understand whether we had omega 6, 5, 8. You can easily see that it's impossible to do it by eyes. But it is also very difficult, let's say, to do it just looking at simple statistical quantities. For example, here I'm showing the scatter plot of the 4th order moment of the velocity module versus the 8th order moment. So we are looking at different moments, and we still see that the scatter plots of this quantity measured over many fields, they are more or less overlapping each other. So there is still a clear separation whether we are below this transition, so the direct regime, or above, but inside one of these two sides of the transition, the statistics is very complex. So we want to understand how we can, using data, and improve our ability to understand what omega is used to obtain these different fields. So let me first say that there are also ways that we can use that are not data-driven based, but there are also equation-informed tools. Like, for example, there is nudging. And the way it works is like that. So let's imagine now we have just one single field and one plane, and we want to see what was the rotation rate for the reference frame for this velocity. So we don't have data, but at least we have to know something, and we know the equation of motion. So we know exactly what are the equation of motion that have generated this field. The only thing we don't know is the rotation frequency of the reference frame. So to understand what is the rotation frequency, we can add an extra term, which is this sort of penalization term. It's a drag term that tries to drive the evolution of this velocity towards the reference value. So adding this term, we can then scan on different omega values to see what is the omega values that is giving us the best agreement between our evolution and the reference field. And here, if we measure the energies, the energy of the difference between the field that is evolving with this nudging equation minus the reference field, we see that we have a clear minimum that is visible when omega is exactly equal to the reference, the omega of the reference value. So it is it's possible for us to understand what is the value, but here we need to perform several simulations to achieve this estimation. Just to open a small parenthesis, this kind of nudging is also useful, for example, in LES. If someone of you is interested in performing large eddy simulations, for example, here we have used, together with Patrizio Di Leoni, this nudging to understand, let's say, to fine-tune the optimal coefficients for subgrid scale models in LES. Like, for example, here we have our nudging large eddy simulations. So we have the same idea. We have Navier-Stokes. We filter the different fields as we generally do for large eddy simulations. And now we need to replace the subgrid scale tensor. And in this example, I'm modeling it using the Smagorinsky closure that, as probably you know very well, this depends on a single coefficients that we need to fine tune. And the way we have chosen this fine tuning was, again, adding an extra penalization term, that is the nudging term, and where this V now comes from a coarse field that was evolved on a fine grid, so it's a fully resolved simulation, and we have seen that this minimum error, the minimum error of so if you integrate the energy of the difference of these two fields, the reference minus V, is obtained when CS is equal to 0.16, which is the value that was generally used in literature. And then, of course, this can be used also to fine-tune different models, and also models that maybe are less trivial, where, for example, you have a non-homogeneity on some directions, and you want to fine-tune the models using this approach. So this is a valid approach, but it's based on the idea that we know the equations. So let's imagine now we want to infer the rotation rate, as we said, just from one plane of the velocity field. And we don't know the equation of motion that have generated these fields, but we have a lot of data. So we have, for each of this plane, we know what was the omega of the simulation. So we have a sort of labeled data set that we can use to train a network. And this is what we do. So we give in input the velocity plane, the velocity module on one plane, and we want to train a network such as it's able to solve this regression problem that goes from the velocity module to the rotation rate of the reference frame. So the network is sketched here. I hope you can see, but the idea is the following. So we have few layers that are convolutional layers. The idea is that these layers need to learn what are the relevant features that needs to be used to then solve the regression task. And then we have this latent vector that is the vector of the features that have been extracted by the convolutions. And then it is coupled by a couple of other fully connected layers up to the output that is the predicted omega value. Then the regression is solved just by minimizing this mean squared error between the true value and the prediction. And we see that the network is indeed able, after training, to minimize this quantity, this error. And the minimization of this quantity means indeed that if we look at the PDF of our predicted value, this becomes almost a delta around the true value of our simulation. So we see that actually the network is converging. So machine learning is not the only way we can solve this problem using data-driven tools. We could also, in principle, use a standard Bayesian inference. So the idea here is that we have to imagine that we know the conditional probability to have a given some values of omega of the rotation frequency, having measured some observables on our planes. So once we have this conditional probability, then we can choose the Bayes inference, the Bayes estimation, as the value of omega that maximizes this conditional probability. So now the problem is, the first problem is to choose an observable that is representative. And here what we have done, for example, we have chosen a velocity module squared, that this is representative for the large scale features of the flow. And also we can combine it with the velocity gradients that instead are representative for the small scales. And also we can use both of them. So we can use the joint probability, the joint conditional probability. Once we have these observables, what we can do, we can, using our training data set, we can try to estimate numerically the conditional probability that for each omegas, give us this value of this observable. And then using the bias theorem, we can invert, such as to get this other inverse conditional probability that is the one we want to have the bias estimation. As we can see anyway here, this is a plot of the joint PDF of velocity module versus velocity gradients squared. And you see that anyway, the PDF for the different omegas are anyway not very well disentangled. So it's not a trivial inverse problem to be solved. So let's see a little bit of results. And here I'm showing a scatter plot. This is just a visualization with some planes and the prediction, the neural network and the bias with respect to the real value. And this is a scatter plot of the true value versus the predicted. So the predicted by neural network versus the true value. And here we see that the hexagon symbols are the mean values over 10,000 different planes that were never used during training, of course. And we see that actually the neural network is quite good in understanding in average, but also the fluctuations. These points here are the scatter plot where the size of points is proportional to the density of points that felt inside this region. And here we see that actually we have not too bad fluctuations and also a good agreement for the mean value. So the neural network was quite good in solving this problem. The bias, on the other hand, using only the large scale features, so the velocity squared is completely blind to this intermediate range of omega values. The situation improves when we look at the velocity gradients, the small scales, which at least at the mean value follows quite well the true value, but the fluctuations are very large. If we even use a more refined bias inference using the conditional probability, the conditional joint probability that combines large and small scale features, we see that actually even bias starts to approach the performance of the network. So it means that the network has learned what is the best observable to put together, mixing small, large scales and all possible measurements that it could have performed, such as to optimize this inversion task. So to give you a little bit the sensitivity of these data-driven tools, let's imagine that now we have planes that have obtained for several different values of omega in our simulations, and now we want to see if our neural network or our data-driven anyway bias or neural network prediction is able to identify what value of omega is equal to the, so what planes have been extracted for a particular reference value of omega. So here we plot on Y the difference between the predicted values minus evaluated, of course, on planes that have been obtained for different values of omega, minus the reference, the value of the reference omega that we want to identify. And here we see that this function indeed has a clear minimum around 1, which is the value where the omega used for the simulation is exactly our reference data. So we see that actually both bias and neural network are able to identify this value, and in particular the neural network has a sensitivity that is a little bit better, so it is more optimized. So I don't know if I still have some time. So just to give you a little bit more quantitative comparison between bias and neural network, what we can do, we can measure the PDF of the predicted values versus the value predicted by the network versus the predicted normalized to the true value. So the perfect prediction would be a delta around 1 at 1. Here we see that these lines are the neural network PDFs, while the histograms are the bias estimation. We can see that both of them tends to be picked around the correct value 1, that is always indicated by the red line. And that in general, anyway, the neural network has a prediction which has tails that are shorter. So in the end, the neural network has a better accuracy. And this is really a quantitative estimation evaluated over 100,000 different planes that were never used during training. So to conclude, we have tried to solve this non-trivial inferring problem on the inferring of the rotational frequency of the reference frame of a turbulent flow. And we have seen that we can do in 2 different ways that anyway are really on the opposite side of the spectrum. Because in one case, we actually can solve this problem without using data. So we just have one single image and we want to understand what was the omega just performing numerical simulation. But that in this case, we are assuming that we know exactly the physics of the problem. And so we have every time we need to perform the exact numerical simulation to minimize the estimation of the rotation frequency. On the other hand, what we can see is that if we don't know anything about the system, but we only about the physics of the system, but we only have data, also in this case, using data-driven, we can solve this problem with a sensitivity, with an accuracy that is very much comparable with the case, with accuracy achieved considering that we know the physics of the system. And in the other case, anyway, we have other pluses and other minuses. So we don't need to perform simulation. So once the network is trained, to get the omega out of one plane is very quick. But before, the training was expensive. So really, now the point is trying to also understand, depending on the problem you have, what is the better tool to use, such as to actually achieve your data analysis. And of course, one can also think to try in the future to combine the two points of view to have even better estimation. So thank you. I will stop.
Thank you very much. Are there maybe online questions we can maybe take first? Nobody's responsible for online questions? No, no question. Okay, then we can have questions from the audience.
Thanks. So just a question like regarding nudging versus data. So the architecture that comes out, do they converge? Because they're trying to do the same physics. One, you're imposing the other side. So the network architecture that results from the nudging and versus the data-driven one, they converge somehow later. I mean, can you? But you impose something by the. Okay, but that results in some kind of hidden architecture because it's a neural network. No. No.
Can you use the microphone, please?
So in this case, there is no neural network. So N is just a parameter, and then you have just to solve a fully resolved numerical simulation where you evolve your field, and you want that your field is as close as possible to a reference value. So they are really two different approaches. They use two different point of views. So the only thing we can say is that they are both, they have a comparable accuracy, but they cannot really be easily compared in terms of approach, let's say, because maybe I will.
Okay.
Yeah, thank you for the nice talk. Could you maybe comment on the sampling strategy you use for the Bayesian inference? What kind of sampler?
Well, we had to choose a few observables, and the observables we chose were the velocity module averaged over the plane, and then the velocity gradients also averaged over the plane squared. Why only these two? Because we don't have the three velocity components. We are assuming to do this inversion only having the velocity module, so we cannot measure vorticity or other quantities. Otherwise, it could have been we could have chosen other observables. And so we just wanted to see how a simple Bayesian inference could work, giving observables that are representative for different scales of the system, that are generally the ones that are more relevant. That's why we chose.
But my question was more on the algorithm side. So what kind of algorithm did you use for the posterior to find the posterior?
Well, we had to compute we had to use the training set for each value of omega that we used in our training data, that we had 10 different values of omega. We have measured the conditional probability of having some values of this observable. So these are just probabilities measured numerically, and then we used this theorem to invert the conditional probability. It was, yeah. I don't know if I.
Yeah, I can discuss. Thanks.
Maybe a similar question. Which is the behavior of convergence of neural network and Bayesian inference in terms of the size of the data set needed to?
Yeah, the data set is very important. I mean, we have done a little bit of this study. For example, we used different resolutions in the data that we used, and I don't have a rate, let's say, that I can say, but I mean, we have seen that if we use a large resolution or more data, the network or the bias are really able to improve their.
They converge in the same
they,
way, or?
Well, let's say the network converges because it has a minimum, it has a loss function to minimize. The bias is more about just measuring this PDF and inverting. So there is not really a convergence. There is a convergence on the accuracy, if you want. And they converge. Yes. I would say I cannot tell you a number. Let's say to be more precise, but they converge in the same way. So data-driven tools, if they have more data, they should to converge better in a similar way. I would say that.
Okay, then thank you very much again to the speaker. We have a second in-person talk. Yeah, so the next presentation will be given by Agnese. That's right, yeah?
Agnese.
Agnese, okay. And the title of the presentation is Structure Interpretation via Neural Networks, an Application to Flow and Transport in Porous Media. Stage is yours.
Oh, yeah. I'm just trying to show the other slide, but it's not working. So,
I think it's the other button. There's one for next and one more.
okay. Oh, thank you. Okay, thank you for the introduction. So in this work, I will talk about the surrogating modeling of flow and transport in porous media. And this work was done in collaboration with the University of Texas at Austin with Dr. Santos and Professor Masha Prodanovic. We are chemical engineers and our co-authors are petroleum engineers. So we are interested in porous media for different applications. For example, we are interested in the packet bed catalytic reactors, and I suggest you to follow my colleague presentation on Friday if you are interested in this kind of applications. Other kind of applications are enhanced recovery, carbon capture and storage, which are more related to subsurface modeling, and also batteries are, and also in batteries, porous media transport is very important since electrodes can be modeled as porous media. And for this, we are involved in a European project about that. So porous media is a very wide application fields, and we strongly believe that physics-based modeling and data-driven models can be used in synergy. As you know, CFD is a bottom-up approach, so we have to solve transport equation, and this can be very time-consuming and computationally expensive. If we use a data set of CFD simulation, it is possible to train machine learning models, and we focus on neural networks in my work, and this can be very useful for multi-scale modeling optimization problems. So this is the workflow that we propose for the training of neural network models starting from a CFD-based data set. And if we know the input features and the output objectives, we can set up a CFD model, and we can solve a number of CFD simulations in order to create a data set and train and test our neural networks. In my work, we used OpenFOAM as CFD tool for solving the simulations. We proved that data-driven models can be used for the surrogate modeling of flow and transport in porous media quite well. And in particular, neural networks can be used for different objectives. For example, they can be used for the prediction of integral quantities. So for the prediction of numbers, we were interested in the prediction, for example, of the permeability or the filtration rate for our transport problem. problems. And it is possible to predict these integral quantities starting from end-selected features. So we choose some input features like the porosity, the mean diameter, or operating condition for the prediction of our objectives. But it is possible also to provide the neural network with the entire geometry of the porous media. And in this way, the network is able alone to understand the most effective features in the geometry for the prediction of the output. So both of these modeling techniques can be employed for the prediction of integral properties very well. In this presentation, I will focus on another problem that can be solved with neural network modeling, and it is the prediction of entire local fields in porous media. So starting from the CFD simulations we solve for the production of the dataset, as I told you, we are interested in flow and transport in porous media. So what we solve is starting from a geometry of a porous media, which is very simple in our application. It's just a bucket bed. We solve at first the Navier-Stokes equation for the evaluation of the flow field, and after on this flow field we solve the advection diffusion equation to simulate the transport of a species inside the porous medium. And we impose a boundary condition on the grain surface, and this can be viewed as a filtration problem if we imagine that the species is a colloid, or it can be just considered as an instantaneous reaction on the boundary of the grains. So what we obtain is a concentration field, and this is what we want to predict with our neural networks. Concerning the dataset generation, in the top table, if you're interested, you can see the range of variation of the features that we employed for the creation of the dataset. And on the right, you can see the range of variation in the resulting dataset of the Reynolds number and of the Peclet number. As you can see, we are in fully laminar conditions, and we explore a quite range of Peclet numbers. This means that we explore a quite range of different transport conditions. We solve these simulations in a single core, and these are the computational times required to solve a single sample for our dataset. I want to show you now instead the architecture that we employ for the prediction of concentration fields. This architecture was conceived by our co-authors for the prediction of flow fields in porous media. And what we do in our work instead is using the same architecture for the prediction of concentration fields. This architecture is made by different scales, and each scale is a fully convolutional neural network, and each scale is fed with some features that are coarsened. This means that each scale accepts as input the feature at a different resolution. In this way, the neural network is able to see different length scales in the input features, and in this way is able to catch the impact of the different scales on his output objective. Sorry. It's not working anymore. Okay. So this is how we trained our multi-scale network. We used, as you all know, GPUs, and we employed our university cluster, which has quite good GPUs for the training of neural network. The memory was enough for the network we were interested in. And as you can see, it is possible to train in a day a quite accurate MSNet for the prediction of concentration fields. And as you know, the time for a new prediction is almost instantaneous. The point we had to solve was which input features are needed by the network in order to predict the concentration fields. And a difference from the prediction of the flow fields that was just a geometric problem. In this case, we have both geometry and operating conditions. So we have to provide the network with the geometry of the porous media and with the operating condition that undergoes in the concentration, in the transport phenomena that we study. So we have to provide the network with the pressure drop across the porous media and with the diffusion coefficient of the chemical species that is transported in porous media. Concerning instead the geometrical descriptor, we tested a range of different features. So we tried to use the Euclidean distance, which is a very common features employed in the porous media field. We tried also the local thickness, which is the last one that, as you can see, is related to the dimension of the pores. But as you can imagine, the concentration field is really related to the inlet boundary of the chemical species. So it is necessary to inform the neural network about the distance from the inlet boundary. And this can be done with a simple linear coordinate variation, or it can be done in a much more descriptive way with this time of flight. And as you can see with the time of flight, it is possible to catch the preferential paths inside the porous media. So our question was, which of these features is the most effective for the prediction of the concentration field? We tried different combination of them. And as you can see, the D solution, which implies the, as obvious, the operating conditions, but the Euclidean distance and the time of flight as geometrical features describing the porous media, is the best set of features. And the average error on the test set of the average concentration in the fields is quite low, is about 3%. I want to show you now some of the predictions made by MSNet for the concentration field. On the left, you can see the CFD result for this sample. In the middle, you can see instead the prediction of MSNet. And as you can see, the concentration fields looks very similar. And we tried to compare in a quantitative way these fields basing on the average concentration inside the porous media and with the profiles in the direction of flow and in the perpendicular direction of flow. I'm going to show you now some other results at intermediate Peclet number, meaning in different transport conditions. And even in this case, the results are quite satisfactory. And even with high Peclet number, the neural network is able to predict quite well the concentration field. So, in conclusion, it is well known that it is possible to use neural networks models in order to predict integral descriptor of the porous media, and convolutional neural networks are very useful for this reason, because we can provide the network with the entire geometry of the porous media. But it is possible also to solve a more complex problem as the local description inside the porous media. And for this reason, for this purpose, it is necessary to train more complex architectures. And it is necessary to choose the most effective features for the prediction of the concentration fields. And this can be useful for all the applications I mentioned you before that implies flow and transport in porous media. Thank you.
Thank you very much for the presentation. Do we have online questions? No online questions. Okay. Then a question.
Just a curiosity, is a reaction, does reaction occur at the interface with the solid?
Yeah, exactly.
Okay.
Yeah.
Okay, thanks.
Yeah.
We have more questions. And then maybe I also have a question. So you said you have for the different features that you have different networks. How do you in the end combine this information? I mean, you said for each CNN you had like a single value output, right?
Yeah, sure. All the features are concatenated, and each scale see a coarsened version of the input features. So we have a coarsening operation of the input features that we feed the neural network with, and then to do the reverse, we have a masked refinement operation. In this way, each scale of the MSNet can communicate and contribute to the final prediction.
Oh, okay. Okay, and then maybe another question. So the geometry is also somehow input to the training, right?
Yeah,
the Euclidean
sure.
Distance, for example.
Yeah, exactly.
So I was wondering how well does this generalize if you consider a different geometry, maybe a different setup of the different balls of force that you have?
Okay, there is the fields prediction I showed you now were on new geometries that were not seen during the training. They were all packing beds, they were not rocks or something completely different, but the choice of the input features was difficult for the generalization problem, because just for the training, understanding, there were not necessary all these features, but in order to be able the network to predict on new geometries, it was necessary to choose very well the input features. So what you have seen are on generalization results.
Okay,
yeah.
Thank you. Ah, there's one more question.
Yes, thank you for the presentation. I was wondering, regarding the geometrical description of the porous media, have you considered to use tortuosity also among the others that you listed? And how does the results compares also to the Darcy's law, for example? Thank you.
Okay. This time of flight, the C, is quite related to tortuosity, because for us, tortuosity is just a number that describes the entire porous media. But with this time of flight, as you can see, we give a local field that is very much related to the tortuosity, because we can see the preferential paths inside the porous media. And this is the reason why the time of flight is more effective compared to the just linear variation, because we help the neural network giving this tortuosity description field. Yeah, and you asked me about the prediction of the flow field, right?
See, regarding Darcy's law in particular.
Okay, this MSNet was originally conceived for the prediction of flow fields, and it works very well, and it's easier because if you work in laminar conditions, it's just a geometry problem. So you just have to provide the geometry with a geometrical descriptor, I mean in that case, and it works very well in this paper, in the MSNet original paper. You can see that they trained on a dataset of just packing beds, and they were able to generalize on rocks. So this multi-scale idea is very useful for generalization problems in flow fields.
Okay, if there are no more questions, then let's thank the speaker again. And the next presentation is a virtual one from Daniel Hilger. And he's giving a presentation on parameterized physics-informed neural networks as surrogate model in shape. Stage is yours.
Yeah, good afternoon. I hope you can all hear me well.
Yes, works.
That's good. I can only see the screen and the back of your head. So, thank you for your introduction. As you just said, my name is Daniel. And I'm going to talk about parameterized physics-informed neural networks and how they can function as a surrogate model in shape optimization. And yeah, I present the work of myself and my students, Stefan and Philip, and I'm part as a PhD student as of the chair for computational analysis of technical system at the RWTH Aachen. When we speak of shape optimization, the question is what shapes do we optimize? And we are in the area of plastic profile extrusion. And before we go into detail about the surrogate modeling and shape optimization, let's first look at the process of plastic profile extrusion and what in general happens. So it's a continuous production process where we process some coarse granulate raw material in an extruder. We heat it up and the extrusion part where we have some screw and yeah, mix our plastic melt and transport it to the main shaping part of the extruder, the so-called extrusion die. And this is the part that is of interest, especially in this talk. Further in the extrusion line, we have the calibration and cooling unit where we cool down and solidify the extruded material, and later pull it off and cut it into like process-specific pieces. So as mentioned, we will deal about talk about shape optimization and especially optimizing the shape of these extrusion dies. Why do we want to optimize these extrusion dies? For that to understand, we first have to understand the special characteristics of plastic melts. And when it comes to modeling these plastic melts, we have to be aware that plastic melts don't show this Newtonian linear correlation between shear stress and shear strain, but we have a nonlinear correlation. And often in plastic melt modeling, we model the behavior via shear thinning models, where we model the viscosity of our material in dependence of the shear rate. And in the rest of the talk, we will do this mainly with the material model proposed by Caro, where we have 3 additional parameters typically fitted with experimental data and yeah, combined with the shear rate. Now to the question, why do we need to optimize these extrusion dies? These special flow characteristics of polymer melts basically lead to also like a certain swelling behavior of the melt after it exits the extrusion die. So if our extrusion die is a square and our goal shape or target shape of the extruded profile would also be a simple square, we wouldn't end up with that, but with this deformed section, cross-section of our profile. So when we design our extrusion dies, what we actually want to have is in the design process, like this slightly deformed cross-section of the extrusion die to in the end up with the product-specific cross-section here, the square. Yeah, the optimization strategy in this process that we pursue is the so-called freeform optimization strategy, where our main goal to use it is basically to limit the number of parameters that we optimize in order to get an obtained deformed shape. How do we do that? We take our computational domain. Conventionally, it's a finite, in our case, a finite element mesh, but for our surrogate model, just a point representation, and we map it onto a unit spline, and the spline is in this case just a parameterized representation of a domain with a few parameters. And we are then able to deform this spline with a limited number of parameters. In this case, it's 2 parameters using some additional symmetry conditions. And we end up with like displaced mesh coordinates or collocation points in our case. And then we invert the mapping to the unit spline to end up the fully deformed computational domain. Typically, we use this optimization approach in our conventional optimization strategy, where we have a local machine and a HPC infrastructure. In our case, it's the RWGH cluster, where we have about 48 nodes, cores per node. And on our local machine, we run our optimizer, which proposes some parameters for our optimization problems. These parameters are used to set up simulation, run the simulation, and then the post-processing is again done on the local machine. And based on that, new parameters proposed. The challenges here in this optimization is especially to keep the number of optimization parameters as low as possible. That's why we use the earlier mentioned free-form deformation approach. Now, we want to, or what we were interested in is, can we replace this HPC computation with a maybe even cheaper surrogate model? And for that, we looked into physics-informed neural networks and maybe something general about pins before we look into the application of extrusions. We have some domain representation by some point set, and we further divide the point set into volume points and boundary points, very similar to finite element analysis. And on the boundary points, we have some known values. Now, we then want to train a function approximator, which is in this case, especially a simple feed-forward neural network. But we extend this feed-forward network by adding some physical information to that. And this physics information is in form of partial differential equations, which uses the output of our network, which are our solution values we were looking for instance, velocity and pressure, and the derivatives with respect to the inputs, so for instance, coordinates or deformation parameters. And based on the PDE and the residual, we can compute from the outputs and the derivatives. We can then use them basically in the optimizer that optimize our neural network to obtain a solution that fulfills the condition of the physics problem. We end up then with some prediction for our problem, as shown here, for instance, the flow around a cylinder. And yeah, we recently published some first results based on that. Now, if we want to apply this approach to the extrusion process, we first extended the state of pin development by introducing the non-Newtonian Carreau model into our pin. And for that, we took a rather simple 2D geometry and tested on that. First, the results were quite satisfactory. So the approximation looked really good compared to a reference finite element solution. And also the error were relatively slow in the dimension of 10 to the minus 5. And the largest error were just in the area where we expected to have the highest velocities. We then extended or further extended this pin approach by using a parameterization of the geometry into or put it into the pin approach. And we did this by combining it with the freeform deformation approach, meaning we have some parameter that is linked to the spline coordinates, and by this spline coordinates, we can deform our computational domain or collocation points and obtain a deformed deformed domain. If we integrated, so we integrated that in our pin, and we ended up with predictions of the flow in these deformed extrusion die shapes, and we were quite happy because the results were quite satisfactory, and again also the error was relatively low. For a reduced order model, we again had some the highest error in areas where we have like the highest velocities. We then tried to use this pin, or we made first attempts to use this pin in an optimization context, as it was the goal from the beginning. And we there used some this setup just presented. We made use of some symmetry, so to display some spline coordinates, and made these parameters to our optimization problem. The object function in this whole optimization problem was basically to obtain the rather uniform velocity profile at the outlet, because experimental findings showed that this is a good measure to obtain a good or reduce the swelling effect. This brings me already to the current state of our research, and which is also kind of the introduction to the outlook, which is basically this more industry, closer to industry example of this L shape, which is like a shape extruded with an industrial application, and this is the test case we are currently working on. The points, the collocation points were generated with the classical meshing tool, so GMesh in this case, and then used to train our pin. To be honest, the results of the first attempts were better than expected. So we actually could get some prediction of the velocity inside this L profile, and we observed the greatest error in our case in the beginning, especially at the outlet. There we made some interesting observation, namely because we used some discretization also used in a finite element computation, where we had a denser distribution of points at the outlet. And actually this denser distribution of the points at the outlet led to some or worse results for the surrogate model. What we then try to have an equal point distribution in the whole L part of the extrusion die, and this actually already generated better results. But this is basically just the latest findings, and we hadn't had time to investigate this further. So this brings me already to the outlook, what we still need to investigate. In general, we need to put some more effort in the training of pins in general. So which hyperparameters are best to set up these surrogate models, how the positioning on density of collocation points for our pin affect the results, and how we can improve the sampling of these points for variation of the domain. Further, of course, there's always some room for improvement with the process model. We can try to implement further boundary conditions that have been used in finite element computation, and consider, for example, the swelling in our model. For the optimization part, we in the end can look what happens if we use more complex cross-section or more hyperparameters, and how this affects the performance of the surrogate model. And in the end, we always have, working with the surrogate model, we always have to ask ourselves the question, is the implementation of a surrogate model, and the training of it was the effort. So do we gain an overall advantage? And with this, I already finished my talk. I can only make advertisement to follow our institute on social media, and where we try to keep you updated about latest research. And with that, I'm happy to take your questions. And yeah, looking forward to the discussion.
Okay, thank you very much, Daniel. No online questions? Questions from the audience? Maybe let me ask you a brief question. I mean, the main intention is to avoid, let's say, the intense use of HPC in this workflow that you have, that you run your simulations and based on the results do your optimization. Have you a rough estimate how much faster this can now be with the integration of the pins in the optimization?
I mean, this is like the part of which I mentioned in the Outlook, especially just in context of optimization, we have to evaluate even if it's fast at all. I mean, as soon as you, like for instance, in process engineering, use it in some control where you have the need for like instant evaluation, there's clearly a benefit of the surrogate models. But this is like really an interesting point we need to answer to ourselves if we overall gain advantage when using this in an optimization context. So this is the question we're still investigating or need to investigate.
Okay, thank you. Was there no question from online? Okay, maybe then another question, when you go to 3D with the representation of your geometry, then you certainly go over to some other kind of splines, right? Like T-splines or B-splines that you then use?
No, in principle, let me just go back to the freeform deformation slide. In principle, it works the same. So yeah, instead, if we go to 3D, we don't have like a spline surface, but a spline volume. But at the beginning, or right now, we're still working with like a simple cube and like a normal B-spline, where we yeah, just have a different positioning or dense positioning of the spline coordinates, but we haven't tried any other type of splines yet. So for now, okay. This works with like simple B-splines.
Okay, thank you very much. If there are no more questions, then let's thank Daniel again. And then we have the last presentation for today. It's also a virtual one. Which will be given by Kartik Kashinath.
So can you see my screen?
Or is that you? Xinfeng Gao?
Xinfeng.
You're the presenter?
Yeah.
Okay.
Yes, I am, sorry. Can you see my screen?
Oh, there was I see there's a change in the program, yeah? Yeah, okay, so never mind, I read it from the screen. Your title is Integration of CFD and Data Assimilation with Deep Learning for Improving Model Parameter Estimation. Stage is yours.
Thank you. Good afternoon, folks in Italy. Good morning and good evening to folks from other parts of the world. Thank you for listening to my talk today. My name is Xinfeng Gao. I'm from Colorado State University. I am going to discuss the integration of CFD and the data assimilation with deep learning to improve model parameter estimation. This work is primarily done by my PhD student Yijin Wang in collaboration with Malaysia Zubansky. In this talk, I want to show two things. First, a preliminary demonstration of how to embed deep learning in the workflow of CFD and data simulation. So since 2014, we have been developed a system of CFD with data simulation, essentially to improve the prediction using experiment data, observations, or high fidelity data. We applied it to reacting flows, turbulent reacting flows for model parameter estimate. So there's a sequence of papers you can find, and also we investigate the different data simulation methods for large scale nonlinear systems that we typically handle in turbulent reacting flows. And the second aspect I want to show is to demonstrate the initial application of this embedded system to a simple problem, how to improve this uncertain model parameter. And you have seen three fantastic talks earlier. They show very beautiful results. And I am going to focus a little bit on the algorithm aspect. How do we embed this component into the CFD and data simulation? So in fact, from the aspect of data simulation, machine learning is a reduced form of data simulation. So they have a commonality here. Both aim to learn about the world using data, using observation. So there's a mathematical foundation for machine learning and data simulation. So that's the Bayes' theorem. It provides an underlying framework to how incorporate information from data to our system. So briefly, the Bayes' theorem, as you all know, is to construct a posterior probability density function of the state based on all the information available so that we find a complementary solution to the estimated problem. So essentially, our goal is to find the posterior PDF based on the prior PDF and a conditional PDF. If they are Gaussian, and then the posterior will be like Gaussian. So we have a form. And then we can take this posterior PDF, we can try to find the optimal state to maximize the posterior PDF. And this is the Q is our control variable, O is observation data, for example. So we can find the maximum posterior estimate, or we can simply find the smallest variance by minimize the loss function. So both will give us the optimal state. And for machine learning and data simulation, so the goal is to reduce the cost function as much as possible by adjusting the control vector. So that's the mathematical foundation, the same. So then why do we combine this data simulation and machine learning? There are a lot of computational tools we can share, toolbox they can use. So the idea is to take advantage of the strengths of both methods. We know data simulation is designed to maximize the utility of information when the data is limited. When the data is scarce, and then we can use the data simulation effectively and also incorporate the constraints from prior knowledge. So we have some physics understanding of the system, and then we can incorporate that to constrain our solution. The strengths of machine learning, it operates really well in the area where we don't have much knowledge. We have little existing physical knowledge to constrain the solution. So if we combine them together, and we can truly get a physics-driven and a data-driven model development. So one of the long-term goals of our research is to improve the subgrid scale model in large data simulation and also the turbulence chemistry interaction models in turbulent reacting flows. And we have done this model improvement just using data simulation. So the next step is we want to see how do we effectively incorporate, embed this machine learning component into data simulation. So how do we combine them? This chart shows two major components here. This is data simulation, and this is machine learning. And then we have two big vectors. So U is your solution vector, state vector. Q is a vector containing the uncertain model parameters, or maybe boundary conditions, all the information that you want to improve the uncertainty you want to learn. So the data simulation can deliver improved state. This improved state will be fed to machine learning algorithm, so it will learn the parameter. The learned parameter will feed back to data simulation component. This is an iterative process. Ultimately, and then we will get to optimize the state, the prediction, and optimize the model parameter. So this flowchart shows the whole algorithm. And the pink box is a deep learning algorithm. So embedded to the system of data simulation and a CFD. So in the CFD and the data system, data simulation system, essentially you have three steps, three major elements. So you have forward model. The forward model is your CFD model. Can be any CFD software. You will use that, predict a flow field, or even finite element software. So you can predict this field, solution field. And then the second step is when you have the data and then you combine them together, try to calculate this innovation. So this is the difference essentially between your model prediction and your available data. Now the next step is taking this difference, you want to find out how do I minimize this uncertainty and then get an optimal state, use the data simulation algorithm. Coming out of this data simulation algorithm, you will have optimal state. So without this deep learning element in the original CFD data simulation system, you take this optimal state, reinitialize the system, you keep going. So when next time when you have data, and then you do the same thing again. But now we want to learn a little bit more. We want to understand better about some regions that we have no idea. So we use this, we embed this machine learning algorithm into it. So here, after come out of this data simulation system, you have updated state. The new state, optimal state, will be fed to this algorithm. This algorithm will learn and then produce output learned model parameter. And then you reinitialize this whole system again, go to your CFD model, forward model, repeat the whole process. So I want to emphasize the two elements, the data simulation and then machine learning. What specifically we're using? For the data simulation, we're using maximum likelihood ensemble filter. This is the ensemble-based filter, DA method. There are a lot of methods available. And for example, variational method, 4D var, 3D var, and also common filter family. There are many methods available, but we needed to consider several things. Your system, your non-linearity. For example, for us, we handle turbulent reacting flows. MLF, based on our experience, has been performed quite well in terms of accuracy, performance, and efficiency. So MLF minimize the cost function by adjusting your control vector. So this is your cost function. This cost function is derived based on the Gaussian distribution. And so on the right-hand side, you have two big terms. So this is your CFD model. of course, can be a finite element, it can be any numerical prediction. So this is the predicted data, and this is your observation or your high resolution simulation data or experiment data. So this is the second term, including their uncertainty and this prediction. And then this blue term is the error covariance. During the data simulation, this blue term couples your model and your data. And then essentially, and then you go through this process, you adjust the control vector, so you can get an optimal state. If your system, your error is not a Gaussian distribution, your cost function will have a different form, but they all follow the same 3 general steps. For the ensemble method, you first initialize an ensemble, and then use your numerical model to propagate to a point there's data available. When data available, you apply data simulation algorithm to find the optimal state. So the optimal state will be reinitialized for the forward model. You continue until the next available data point. So this is the data simulation algorithm method we're using. And then for the machine learning, deep learning algorithm, we just use the simple artificial neural network for now. This is the supervised learning. And today we're so fortunate that there's so many machine learning algorithms out there we can leverage. So we use TensorFlow, and it's the more computationally efficient and capable of learning or nonlinear relationships between input and output. So we basically train this network, and now we try to estimate the parameter. Now, I just want to demonstrate a simple test problem, the convection diffusion reaction model. This is a simple partial differential equation, as you can see, but we always want to start from very simple. We can understand each step in the algorithm, make sure we have a high confidence we're getting things right. So in this demonstration, we're trying to estimate the model parameter C. So we assume the C is an uncertain parameter. In fact, we know the value, but we use this C as the example. And this is a nice model, simple, still shows 3 physical processes as many fluid dynamics problem. You have a convection, you have diffusion, and a source. And this figure simply shows what is the solution distribution, spatial distribution over time. So from time 0 to infinite time, eventually the solution will be 0 in the domain. So we know the analytical solution. Essentially, in this whole system, you have 3 big components you need to configure. So the CFD, this is the 1D. We use a simple problem. This is 64 cells. This is the finite model method. It's a 4th order accurate. 64 cells is pretty sufficient. We have 4th term. For this case, we know the model parameter true value, so that we can assess whether our model parameter estimate the accuracy. And then we have analytical solution as well, so that we can assimilate this data into the data simulation component. For the data simulation, there are several factors we need to set it up. What is the ensemble size? For example, we have 10 members in this case. We have 1 control case. In the control vector, we of course include our model parameter. It's 1 model parameter. If you want to estimate more, and then you put them all in this control vector. So this and then including the state vector as well. We basically randomly select initial values for C, 10 Cs in this range from 0.5 to 5. So we perform 15 DA cycle. And for the network, we use the simple 2 hidden layers, 40 neurons, about 2,400 parameters. Importantly, to point out the training samples is 500 sets of CFD data. So we basically a combination of different parameters at different time point. This is a transient problem. So we choose the solution between this two time point. Now let's see how it does here. And this figure, in this figure, it shows the parameter estimate of C, the trajectory over the DA cycles. So we have 15 DA cycles. And then we know the truth is dashed line. Truth is what? Constant, 1. Now, for the 3 different symbols, the black is deep learning. Just do a deep learning based on those ensemble. We estimate the parameter. As you can see, over the this time, it converges to state values much higher than the true value. And then the data assimilation, the red, and then data assimilation converges after it's quite a nice up at the 15 DA cycle. And then we know it's going to converge. We use this problem for a long time. We know this behavior. And then for the coupled data assimilation with deep learning, as you can see at the beginning, it is slower, DA much faster. But approaching the 15 DA cycle, the data assimilation and the machine learning algorithm give us very similar results. And this is converted, this is a C value estimate. And we look at the error. So this error distribution along the spatial location. And then the green is combined. The red is DA. And then you can see that for each point, the data assimilation actually give you a lower error. For this simple example, this is what we expect. What do we want to see? DA is always doing good if we use this particular setup. Is better than data assimilation machine learning. But we have different cases that where the combiner can do better, improve. And if you look at this on the left-hand side, and this sigma square is the variance. The variance for C, the C is for the ensemble, actually for the ensemble. So you have 10 members. So the variance drops quite a large in that combiner algorithm. So this give us some kind of indication that we needed to look for the immediate next step. Want to look at a more complicated problem. We know that the neural network is really sensitive when you train that. And also when you do the observation, so data assimilation, use the data for observation. We want to artificially change the information we know, the quantity. And then we want to conduct a performance between the data assimilation alone and the coupled system. We want to know where the coupled system, the deep learning can really help in the physics. So this essentially shows that we have a algorithm now. We know how to embed deep learning in our CFD data assimilation system. And then the next step we're going to apply to understanding the model parameter error, because the model parameter, how the error evolves, that's the area that we don't know. We lack knowledge. We lack the physics understanding. Those parts can benefit deep learning. And data assimilation can already do well when we have a base model. So this is the next step. I would like to thank our sponsors, National Science Foundation, particularly for computational data enabled science and engineering from the mathematical and physical division. And also would like to thank support from Air Force Science, Air Force Office of Scientific Research. And this is the application case for reacting flows. So I'll stop here, and I would like to answer your questions and have some discussions if you're interested in the algorithm aspect. Thank you very much.
Thank you very much for your presentation. Again, my question, online questions? No, okay. Questions in the audience?
Yeah, thank you for the talk. Yeah, my question is on how you ensure that you have enough data to train the deep learning model, since you are in your loop you are dependent on the Bayesian inference to provide this data, right? And this model is, I mean, it's computationally expensive since you need the forward model to run this, and it's also not easily parallelizable. So how do you ensure that you have enough data to train the deep learning model?
Right. So for this case, we typically use ensemble-based data assimilation. So here, we have ensemble different cases. But you are correct, for larger system like reacting flows, each case is already expensive, so we cannot really afford a lot runs. But what we actually can also do this, I didn't show it here. In our system, we have two different numerical techniques there at different resolution. We have adaptive mesh refinement on different mesh we can learn, and also we have a multigrid process. So essentially, this multigrid also we have a space-time. We have a lot of space-time slices at a different time. So we harvest those information during this solution process. So we feed those information to machine learning component, in addition to this example, the original example case. Does that help answer the question? So yeah. Absolutely, in order to learn to have enough data for the machine learning component. So we basically use this multi-resolution, multi-grid, and also we have multi-model. In the process, we embedded the DNS into our largest simulation, and then including the example information. We try to get as much as possible to feed it to the machine learning. So this is still the interesting part is how do we constantly make sure the information is sufficient. Thank you for the question.
More questions?
Yeah. Sorry, I missed the beginning of your talk. So is this a steady state system you're modeling? The data assimilation is on a steady state?
It's unsteady. So we do many problems. We can do a steady, unsteady, statistically steady. So any kind of type of problem can. That's no problem. It's just depending on your data. If you have a steady state problem, for example, we did a turbulent reacting flows, which has a steady state. Statistically problem, so you can assimilate the time averaging data into your system. But if you have a transient problem and you assimilate the instantaneous data into your system.
So your DA has to continuously inject back, right? If it's an unsteady, because it'll diverge after some time, like weather forecasting. I mean, if you do just DA today, it'll diverge after 5 days or something like that.
Right. But here, so the difference from forecast, weather forecast is that for example, we're not just focused on initial condition, right? We have whenever there's a data available, we try to use the data to help our CFD. If there's no data available, you're just doing the regular CFD prediction.
Okay, thank you.
But you're correct that if the model parameters, a lot of uncertain parameter in the system, and then whether it's a free CFD or combined with data simulation, we always have to worry about the solution accuracy. But here is kind of with the base CFD, and then can we use the extra information to help us improve the accuracy when the data is available?
Okay, maybe a final question from my side concerning here the cost function that you've just shown. you equally weight the CFD part and the data part. Why is that?
Actually, this is there's no weighting. So I think the implicitly incorporated in the forecast error covariance and then the experimental error covariance. So this will play a important role. This is coming from the Gaussian distribution. So that's not weighting, equal weighting. They based on the ratio between the uncertainty from CFD and then the uncertainty from the experiment data. Sorry, I should clarify this. It's just this big bulk term, and then all this you said here. This one's a forecast error covariance. This is the uncertainty with experimental data.
Okay, thank you very much. So no more questions then. Let's thank the speaker again, and also I would like to thank all contributors to the session and the audience for very interesting questions. And then with this, I close the session and hopefully see you tomorrow afternoon in our next session.